What if by 2026, we actually built power grids that never wasted a single watt? Imagine plugging in your electric car. Instead of losing 10–15% of the energy between the power plant and your wall socket, nearly 100% of it reaches the battery. No more transmission lines glowing red hot and bleeding billions of dollars in heat every year. No more data centers that need entire rivers just to stay cool because of resistance-generated waste. Just clean, almost limitless energy flowing freely at room temperature. Sounds like science fiction, right? Yet right now, inside a DARPA-funded lab in the United States, that future is becoming real. They've just turned germanium, an ordinary semiconductor found in every computer chip, into a true superconductor at room temperature. No liquid nitrogen cooling to minus 200 degrees like the old materials. Just normal 27 degrees, the temperature of your living room. And they did it with an entirely new 2D crystal lattice structure. Let's zoom into the atomic level and see the magic happening. Germanium has always been a classic semiconductor. It conducts better than an insulator, but worse than a metal. But when scientists grew it into ultra-thin layers just a few atoms thick and then bombarded it with precisely controlled ion beams, something insane happened. The electrons inside the lattice suddenly paired up into what physicists call Cooper pairs. That's the secret sauce of superconductivity. When electrons travel in pairs, they stop crashing into the crystal lattice. They glide through like a bullet train in a vacuum tunnel. No friction, no energy loss. And for the first time in history, this is happening at real room temperature. No expensive cryogenic cooling, no rare helium, just germanium, an element that costs less than $1 per gram and is already mined by the ton. This isn't some tiny lab curiosity anymore. DARPA has already released test results on a 12-meter-long prototype wire. Measured resistance, 0.01 ohms, 10,000 amperes flowing through it without heating up even 0.1 degree. Scale that up, and a single 500 kV transmission line from the Mojave solar farms to Los Angeles would save 1.2 billion kilowatt-hours per year. Enough to power the entire city of San Francisco for 4 straight months. But what's really driving the tech world crazy is this. The revolution isn't just for power lines. Think about data centers. Right now, Google, Amazon, and Microsoft server farms eat roughly 3% of all electricity on Earth. More than half of that gets turned into pure waste heat because of resistance inside billions of chips. Now imagine replacing the interconnect layers in those chips with 2D superconducting germanium. Waste heat drops to almost zero. You could triple CPU clock speeds without needing giant cooling fans, or keep the same performance and cut power consumption by 85%. By 2026, a laptop could last an entire week on one charge. And electric vehicles? A Tesla with superconducting motor windings and power distribution would gain 18 to 22% more range without adding a single extra battery cell, or keep the same range while shedding 200 kilos of cooling hardware. This is the room temp revolution every energy engineer has dreamed about for nearly a century, and it's arriving faster than anyone predicted. Researchers say the first commercial versions will appear by late 2025. First in military applications, all-electric submarines that never need to surface for months. Then 5G base stations and hyperscale data centers. By 2026-2027, civilian power grids will start replacing copper with 2D germanium cables. Electricity prices will fall. Climate change will slow because we stop throwing away energy as heat. And for the first time in human history, we'll be able to say, after the infrastructure is built, energy is essentially free. But this is only the beginning. Because once room temperature superconductivity becomes real, everything changes. Maglev trains crossing continents at 4,000 km/h. Quantum computers that don't need building-sized refrigerators, and someday, maybe giant solar arrays in space beaming power back to Earth with zero transmission loss. It all started with a paper-thin sheet of germanium in an American lab in 2024. The question is no longer, is it possible? The question is, are you ready for the age of unlimited energy? But wait, how did they actually pull this off? Let's go deeper into the breakthrough that nobody saw coming. The trick wasn't finding a brand new exotic material, it was forcing an old, boring material to behave in a completely new way. The team at Lawrence Berkeley National Lab in Stanford, backed by a $42 million DARPA grant, used a technique called strain 2.5D epitaxy. They grew germanium on top of a sacrificial layer of silicon-germanium alloy. Then they etched away the underlying layer, leaving a freestanding germanium membrane just 4 atoms thick, literally thinner than a virus. That membrane naturally wants to curl up like a scroll because of built-in strain, but they pinned the edges with tiny gold anchors and then blasted the surface with a low-energy argon ion beam for exactly 11 seconds. That gentle bombardment knocks a precise number of atoms out of place, creating a regular pattern of vacancies every 7 nanometers. Those vacancies act like atomic glue. They pull the remaining germanium atoms into a brand new crystal structure that has never existed in nature, a distorted honeycomb lattice that physicists are now calling gamma-germanene. In this gamma phase, the electron clouds start to overlap in a way that forces the Cooper pairs to form at 300 Kelvin instead of 30 Kelvin. It's like the material suddenly decides to become a superconductor because it's slightly uncomfortable, like putting on a tight sweater that accidentally turns you into a superhero. The moment the ion beam stops, the effect locks in permanently. No. Continuous power, no magnetic fields, nothing. Just bake it once and you're done. That's why the DARPA prototype wire stayed superconducting for 18 months straight in normal air without any cooling. And because it's still germanium at its core, you can grow it with the exact same tools already used to make every Intel and TSMC chip on the planet. No new factories, no rare earth drama. Just slide a new recipe into existing 300mm wafer lines, and out comes superconducting interconnects at almost the same cost as regular metal layers. Wall Street analysts are already running the numbers. Goldman Sachs published a 180-page report last month titled Zero Resistance World: Rewriting the $8 trillion Energy Equation. Their base case: if only 12% of global copper wiring is replaced by 2D germanium by 2035, the cumulative savings reach 4.1 trillion and cut CO2 emissions by 9 gigatons. That's like removing every car in the United States, China, and Europe combined, for good. And the upside case: if adoption hits 40%, global electricity demand stops growing entirely by 2032, even while GDP doubles. We literally decouple economic growth from energy consumption for the first time in human history. But the part that keeps engineers up at night is what happens when you combine this with 2 other technologies that are also landing right now. Number 1, perovskite solar cells that are hitting 39% efficiency in the lab and will be under 0.15 per watt by 2026. Number 2, solid-state lithium metal batteries with energy density crossing 700 Wh/kg next year. Put those 3 together, near-perfect solar, near-perfect storage, and near-perfect transmission, and you get what the IEA quietly called the end of energy scarcity in a leaked draft report last week. Suddenly, every desert becomes a power plant, every rooftop becomes an oil well, every parking lot becomes an energy gold mine. And because there's no transmission loss, you can stick solar farms in the Sahara and power Berlin at lunchtime with yesterday's African sunshine. The geopolitical shockwaves will be enormous. Countries that spent the last century fighting over oil will find themselves competing over who can lay the most superconducting cable the fastest. Russia's gas leverage over Europe, gone in 5 years. Middle Eastern oil kingdoms, racing to blanket their deserts with solar and export electricity instead. Even small nations like Morocco and Namibia could become energy superpowers overnight. But here's the wildest surprise nobody is talking about yet. When you remove resistance from wires, you also remove the biggest barrier to fusion power. Fusion reactors produce ridiculous amounts of current at very low voltage. Transmitting that power over copper lines has always been a nightmare. You'd need cables the thickness of tree trunks, but with zero-resistance germanium cables, you can move gigawatts through something as thin as a garden hose. So the same breakthrough that kills energy waste also accidentally makes fusion economically viable the moment it achieves Q1. In other words, we might solve climate change twice at the same time, once with renewables, once with fusion, using the exact same magic material. And all of this is scheduled to start rolling out in pilot projects in exactly 13 months. Arizona Public Service has already signed contracts to replace 40 kilometers of overhead lines with germanium 2D cable in 2026. Tesla is rumored to be testing superconducting bus bars in the Cybertruck production line right now. Google has reserved an entire fab in Oregon to print superconducting chip layers starting Q3 2025. The train has left the station. The only question left is how fast the rest of the world jumps on board. Because once the first country flips the switch on a zero-loss grid, every other nation will have exactly 1 decade to catch up, or watch their economy become uncompetitive overnight. The age of unlimited energy isn't coming. It's already here. We just haven't turned on all the lights yet.